Welcome to the Survival Bunker, where we study the brutal reality of surviving war zones, sieges, and battlefield collapse. The Pentagon's most expensive bombs are meeting their match against a specialized mineral fortress. While traditional bunkers crumble under kinetic pressure, Iran's ultra-high-performance concrete is deflecting massive penetrators back at the source. Today we dissect the molecular chemistry turning Iranian mountain bases into structures that defy modern ballistics. In 2022, Iran publicly revealed Eagle 44, a subterranean airbase carved directly into mountain bedrock, capable of housing and launching fighter jets from tunnels extending hundreds of meters into the Zagros mountain range. Iran's tunnel warfare doctrine, developed progressively since the Iran-Iraq War of 1980 to 1988, has produced a network of hardened underground installations across the Zagros and Alborz ranges that Western intelligence agencies have spent decades attempting to fully map. Standard aerial surveillance identifies surface entry points but cannot determine the structural composition of the mountain itself. This is the first layer of strategic advantage. The mountain is both the camouflage and the armor. The distinction that matters militarily is the difference between standard industrial concrete, which achieves a compressive strength of roughly 30 to 40 megapascals, and the ultra-high-performance concrete now documented in Iranian military construction, which achieves compressive strengths between 150 and 250 megapascals. That is not an incremental improvement. It is a fundamentally different material class. Ultra-high-performance concrete, UHPC, derives its structural characteristics from three interlocking components: a high-percentage quartz aggregate, a dense silica fume matrix, and a suspension of micro-steel fibers throughout the mixture. The quartz aggregate creates a density profile that approaches natural granite while retaining controlled flexibility under load. Unlike standard concrete, which is essentially a brittle matrix that fractures in tension, UHPC's silica fume fills the microscopic voids between cement particles, producing a near-homogeneous slab with minimal internal fracture pathways. When kinetic energy strikes this surface, it cannot exploit the micro-crack networks that conventional penetrators depend on to propagate destruction inward. The micro-steel fiber suspension is the second critical element. Steel fibers distributed throughout the concrete matrix intercept crack propagation at the microscopic level. When a shockwave travels through standard concrete, it accelerates along existing fracture lines, the spalling effect that causes secondary internal explosions. In UHPC, the fiber network arrests crack growth before it reaches critical propagation velocity. The energy is distributed laterally across the entire slab surface rather than channeled inward toward the structure's core. The result is a material that absorbs, distributes, and partially reflects kinetic energy rather than transmitting it. The GBU-57 Massive Ordnance Penetrator was designed around a specific physics assumption, that the target material would decelerate the weapon's nose cone at a predictable rate, triggering the delayed action fuse at the correct depth for maximum structural damage. The weapon carries a 2,400 kilogram warhead, and is the heaviest precision-guided munition in the U.S. arsenal. That deceleration assumption breaks against UHPC. The extreme surface hardness generated by the quartz aggregate, harder than the steel alloy of the penetrator nose cone itself in specific impact geometries, deforms the weapon's tip on contact. A deformed nose cone no longer penetrates in a controlled trajectory. It deflects, tumbles, or loses the velocity profile required to trigger the fuse at operational depth. Declassified assessments from the U.S. Government Accountability Office, published in 2012 and updated in subsequent defense posture reviews, acknowledged that certain hardened Iranian facilities presented penetration challenges beyond the GBU-57's confirmed capability envelope. Iran's geographic positioning inside the Zagros mountain range amplifies every defensive advantage UHPC provides. The mountains supply natural overburden, the rock mass above a tunnel that any penetrator must breach before reaching the constructed walls. Effective overburden at key Iranian facilities is estimated between 60 and 80 meters of natural rock before the engineered concrete begins. The UHPC fortification of a tunnel entry costs a fraction of that figure. Iran manufactures the quartz aggregate domestically from Zagros geological deposits. The defense gets cheaper. The offense does not. The 2026 defense technology landscape has produced two theoretical responses to UHPC fortification: laser-guided thermal drilling systems that melt rather than shatter target material, and thermobaric munitions delivered through existing tunnel openings rather than through walls. Neither eliminates the problem. Thermal drilling systems require sustained targeting dwell time that contested airspace cannot guarantee. Thermobaric delivery requires open tunnel access that Iran's layered blast door systems are specifically designed to deny. The battle for air superiority has descended from the sky into the molecular composition of the Earth. The side that controls material science now controls survivability. Iran identified this decades before Western doctrine acknowledged it. If this briefing changed how you understand modern defensive engineering, share it with someone who needs to. Subscribe to the Survival Bunker and hit the notification bell. Every week we break down the hard science, history, and tactics that define who survives and who does not.